This time we are examining the insulation in the professor's house. So we have the dimensions for the professor's house and they are given in feet squared, and I've converted them to meters squared because using feet is kind of gross. And he gave us the R value in imperial units, which is feet squared per degrees Fahrenheit per hour per BTU. And I also took the liberty of changing those into metric units, so now they are given in meters squared per Kelvin over watts. Today he wants to figure out if he can increase the insulation in his roof from 2.2895 to 6.3403 by adding cellulose, which has a thermal resistance of 0.61641 per inch. And the reason I left this in per inch is because the professor would like to know how many inches of cellulose are needed, because he can't go down to the hardware store and buy centimeters of cellulose, I suppose. I have drawn a little model of this where it shows that the outside temperature is 130 degrees F and the inside is 80 degrees F. And we have the R equals 13 initial wall paired with the R equals 3.5 per inch added segment of wall, which is what we are trying to find out. And so from there, I made a little equation, which is RL equals 13 plus 3.5L, which looks like the little graph below it. And the reason I made this is to show that this is a really easy relation when it comes to something like this. You can just turn it into an equation fairly simply. It's just a simple process, and you can use that to solve for it. And I did, except I did it in the metric units. So it's 6.3403 minus 2.2895 over 0.61641. And what that leaves you with is 6.57 inches. And so all you need to do to make his roof insulation almost 3 times as thick is just add a few inches of cellulose, which isn't even that many. Now we would like to compare the rate of heat transfer before we added the insulation and after we added the insulation. So first things first is you're going to want to convert from Fahrenheit to Kelvin. And for this problem in particular, if you want to do all of this in imperial units, it would have probably been entirely possible. But in general, when you have the rate of heat transfer equation dq for dq dt, you do not want there to be negative temperatures, because negative temperatures are going to tend to break the problem. So in most cases, you're going to want to convert to Kelvin, because Kelvin is set so that absolute zero is absolute zero and there's no negative degrees of temperature. So we find the attic is going to be approximately 327.59 degrees Kelvin, and the inside is going to be 299.8 degrees Kelvin. And these are fairly simple to find as long as you assume the temperature of the attic is 130 degrees Fahrenheit and the inside of the house is 80, which should be about typical for a really hot day in California where the professor lives. So we use the rate of heat transfer equation, dq dt equals A over R delta T, and Q is going to be in units of energy, T is time, so dq dt is quite literally energy over time, is equal to the area over the resistance, or R value, delta T. So most of these things are pretty self-explanatory. The area of the professor's house is given in the dimensions of his house is 136.01 meters squared. The resistance before he adds insulation is given as R equals 13, converted to metric units gives you 2.2895. And the delta T is simply the temperature of the attic minus the temperature of the inside of the house. So you get 1650 joules per second without insulation added. So after you've added the insulation to get it up to 6.3403, you will have a heat transfer of instead 595 joules per second. So we can convert both of these into BTU using a pretty simple equation, and we get, for the less insulation case, 1.564 BTU, and for the more insulation case, we get 0.564 BTU. So it's pretty clear just by looking at these two numbers that the difference is approximately a factor of 3, and the case where we have more insulation causes the heat transfer to be about 3 times as slow, which can be very beneficial in places where temperatures are more extreme. And places like California or places where it gets very cold also would be very much affected by the addition of insulation. Another thing to consider is that it kind of just makes sense that the difference is about 3 because the R value is different by about 3, and the R value is really more of a proportionality constant than anything else. So typically, as long as you have an idea of what the R value is, you'll have an idea of what the difference in the rate of heat transfer is. So I think that's all for this problem. So goodbye.